Everyone assumes that green hydrogen will succeed wherever renewable power is cheapest. It sounds logical. If electricity is the biggest cost input, then regions with abundant solar or wind should naturally produce the lowest cost hydrogen. This assumption has shaped national strategies, investment flows, and press releases across Africa, the Middle East, Australia, Latin America, and parts of Asia. Cheap power equals cheap hydrogen. On paper, the math looks irresistible. In reality, that assumption is quietly killing green hydrogen projects around the world. What's happening is not a failure of technology. Electrolyzers work. Solar and wind work. Hydrogen can be produced cleanly. The failure is systemic. Green hydrogen is not an electricity problem. It is a utilization, infrastructure, and integration problem. And those problems are most severe in the very regions that were expected to win. The core misunderstanding is simple but profound. Energy systems do not fail because inputs are expensive. They fail because assets are idle, mismatched, or poorly integrated. Green hydrogen exposes this reality more brutally than almost any other clean energy technology. Cheap electrons alone are not enough. What matters is how often those electrons can be used, how reliably they can be delivered, and how efficiently the rest of the system can operate around them. At the center of this issue is capacity factor. Electrolyzers are capital-intensive assets. Once they are installed, their economics depend overwhelmingly on how many hours per year they run. A high-utilization electrolyzer spreads its fixed costs across a large volume of hydrogen. A low-utilization electrolyzer produces expensive hydrogen no matter how cheap the electricity is. This is where the cheapest power regions often fall apart. Many of the lowest-cost renewable regions have highly intermittent generation profiles. Solar peaks sharply during the day and disappears at night. Wind surges unpredictably and can remain low for extended periods. Seasonal swings can be extreme. From a grid perspective, this intermittency can be managed with diversity, storage, and transmission. From an electrolyzer perspective, intermittency is deadly. An electrolyzer that runs only when excess power happens to be available is an electrolyzer that spends most of its life idle. This leads directly to the capacity factor trap. A solar resource with world-class economics might deliver electricity at $20 per megawatt hour, but only for a fraction of the year. If an electrolyzer attached to that resource runs at 30% utilization, its capital cost per kilogram of hydrogen explodes. Suddenly, the cheapest power in the world is producing some of the most expensive hydrogen. The problem is not the price of electricity. The problem is the hours. This is where many green hydrogen models quietly break. They assume high utilization without explaining how it is achieved. They assume electrolyzers can run whenever needed without addressing intermittency. They assume grids will magically absorb variability. In practice, those assumptions collapse quickly. Curtailment is often presented as the solution. The idea is seductive. Renewable energy is sometimes wasted because the grid cannot absorb it. Why not use that free electricity to make hydrogen? The flaw is that curtailment is not a reliable energy source. It is sporadic, unpredictable, and unbankable. You cannot finance a multi-hundred million dollar hydrogen facility on leftover electrons that appear and disappear without warning. Curtailment also occurs precisely because systems are misaligned. Transmission is constrained, demand is distant, storage is insufficient. Using curtailment for hydrogen does not fix these problems, it inherits them. An electrolyzer fed by curtailment operates at extremely low utilization, producing hydrogen intermittently and expensively. From a project finance perspective, this is not a strategy, it is a gamble. Grid weakness compounds the problem. Many regions with cheap renewable power lack robust transmission infrastructure. Power may be abundant at the generation site, but unusable beyond it. Voltage stability can be poor. Frequency deviations can be significant. Electrolyzers are not tolerant of dirty power. They require stable, high-quality electricity to operate efficiently and avoid degradation. Upgrading grids to meet electrolyzer requirements often costs more than the electrolyzer itself. Transmission lines, substations, and grid reinforcement can dominate project capital expenditure. In some cases, developers attempt to bypass the grid entirely, building off-grid hydrogen systems. This introduces new costs in the form of oversized renewable capacity, energy storage, and power conditioning equipment. Once again, cheap power at the source leads to expensive systems overall. Water availability introduces another overlooked constraint. Many regions with excellent solar resources are arid. Electrolysis requires water of high purity. Treating seawater or brackish water adds energy use, complexity, and cost. Transporting water inland or hydrogen outward compounds logistical challenges. These costs rarely appear in headline hydrogen price estimates, yet they materially affect real projects. Compression and storage further erode the cheap power narrative. Hydrogen must be compressed, stored, and often transported before it can be used. Compression alone consumes a meaningful share of the energy embedded in hydrogen. Storage systems add capital cost and efficiency losses. If hydrogen must be moved long distances from cheap power regions to demand centers, transport costs can overwhelm production savings. Cheap power in the desert does not help if demand lives on the coast or in industrial corridors hundreds of kilometers away. This leads to a fundamental systems insight. Green hydrogen does not want cheap power. It wants consistent power. It wants predictable demand. It wants strong infrastructure. It wants integration, not abundance. Fossil fuels are forgiving. They tolerate inefficiency, losses, and idle capacity. Hydrogen is fragile. Small inefficiencies compound rapidly. Minor misalignments destroy economics. Yet announcements continue to pour in from low-cost renewable regions. Why? Because early hydrogen projects rarely fail immediately. Subsidies mask weaknesses. Pilot scales hide utilization problems. Political incentives reward announcements, not long-term performance. Early years often look promising with low marginal costs and generous support. The real problems emerge later as maintenance increases, subsidies taper, utilization disappoints, and offtake fails to materialize at scale. This is why many green hydrogen projects appear profitable in year 1 and struggle by year 3. Fixed costs remain, utilization underperforms, operating complexity grows. What looked like a power-driven success story reveals itself as a system-level failure. The irony is that green hydrogen often performs better in places where power is not cheapest. Regions with higher electricity cost but stronger grids, steadier demand, and industrial integration can outperform low-cost regions on a delivered hydrogen basis. When electrolyzers run consistently, when off-takers are co-located, when infrastructure already exists, hydrogen economics stabilize. Cost per kilogram becomes predictable. Projects become financeable. This does not mean cheap power regions are doomed. It means they must design systems differently. Hydrogen projects that succeed in these regions tend to integrate generation, storage, electrolyzers, and demand tightly. They prioritize utilization over headline electricity prices. They co-locate production and use. They accept higher initial capital costs to achieve operational stability. The lesson is uncomfortable because it undermines a central talking point of the hydrogen transition. Cheap renewable energy alone does not create cheap green hydrogen. Systems do. Until this reality is acknowledged, capital will continue to flow into projects that look attractive on slides and struggle in operation. From a sustainability perspective, the implications are serious. Idle electrolyzers waste embedded emissions. Oversized renewable plants increase land use without proportional output. Poorly utilized hydrogen systems deliver fewer climate benefits than promised. Sustainability is not just about clean inputs. It is about effective deployment. For policymakers, this demands a shift in incentives. Rewarding capacity announcements is easy. Rewarding utilization, integration, and performance is harder but necessary. Hydrogen policy that ignores system behavior risks producing expensive, underperforming assets at scale. For investors, the signal is clear. Ask not where power is cheapest, but where systems are strongest. Ask how many hours the electrolyzer will run. Ask where the hydrogen will go. Ask what breaks when subsidies fade. These questions matter more than headline electricity prices. For developers, the message is both sobering and empowering. Green hydrogen can work. but it works only when designed as part of a coherent energy system. Cheap power is an input, not a solution. Without alignment across generation, infrastructure, and demand, it becomes a distraction. Green hydrogen is not failing because renewables are too expensive. It is failing where power is cheapest because systems are weakest. That is not a contradiction. It is the defining challenge of the hydrogen transition. The future of green hydrogen will belong not to the regions with the lowest solar bids, but to those that understand utilization, integration, and execution. Hydrogen succeeds where systems are designed, not where power is merely abundant. If there is one lesson to take forward, it is this. Stop asking where electricity is cheapest. Start asking whether the system can actually run. That question will determine which hydrogen projects survive, which fail quietly, and which shape the next phase of the energy transition.